Well, today I'm really glad to get to share something with you that I've been working on for the past 15 years. But more importantly, something that could become the first specimen of an entire new industry that we might find all around the planet over the next decades. Think of it as something like the very first smartphone, still quite clumsy and quite expensive, but of transformative technology. Smartphones have changed the way how we communicate. This, I hope, could change the way how we deal with global warming. This is Orca. This is the first worldwide commercial direct air capture and storage plant. It is in Iceland, and it is an industrial plant that extracts CO2 out of ambient air. We have operated now for more than 1 year. It costs more than $10 million to build Orca. And its modules, those 8 boxes that we call CO2 collectors, they are designed to extract a bit more than 10 tons of carbon dioxide from the air every day. It sounds quite expensive. However, when thinking about cost, we should keep in mind one thing. There is one thing that we cannot buy, and that is time. And we need to be quite fast here. So that is why Orca is not there to demonstrate costs. Orca is there to show in the field, out there in the weather, that the plant is operating and Orca is working. So the next step for us at Climeworks and for all the other companies in the field is now going forward, improving the technology, scaling it up from tens to hundreds to millions of tons capacity. And as we go ahead and we scale it up, with every new plant going online, we'll have efficiencies going up and we'll have costs going down. Now, how does it work? In the case of Orca, we have fans mounted to the CO2 collectors that draw air through them. Inside, there is a filter material that we call sorbent, a highly porous material. And as the air pulls through it, the CO2 is bound at the surface of this material. Think of it as a sponge that sucks up water in its pores. We do that for a certain time until the material is filled with CO2, it is saturated. And we close the modules, we heat them up to around 100 degrees Celsius, and we can extract concentrated CO2 from them. The good thing is that the main energy input that we need for that process is low temperature heat at around 100 degrees Celsius. And it can entirely be powered by renewable energy. Now, that looks quite easy at first glance, right? And indeed, the process behind that is quite simple. However, when it comes to implementing that into reality, in the field out there, with the purpose of having a plant that is constantly operating 24/7 reliably, then it becomes quite challenging. Let me give you 2 examples why it is a challenge to capture and remove CO2 from the air. First of all, there is not a lot of CO2 in the air. We're currently at around 420 ppm. That means 1 molecule out of 2,500 molecules in the air around us is CO2. That's not a lot. And that means to extract only 1 ton of CO2 from the air, we need to filter around 2 million cubic meters of air. That's about 800 Olympic swimming pools. And there's another way of picturing that, which I personally find quite puzzling. Imagine one of these filters with an inlet area of 1 meter by 1 meter. And the amount of air, like think of it as a block of air that you have to push through that filter inlet to take just 1 ton of CO2 out of the air, is 2,000 kilometers long. Another example why this is a challenge is that it is not so easy to find good, actually the best sorbent materials, which are both high-performing and which can prevail outside there in the field with a long life. Now, on this next picture, you see Christoph and myself, co-founders of Climeworks, in the very early days of Climeworks, working on that. The very first sorbents, we produced them with our own hands, such as you would do your laundry if you didn't have a washing machine. We set some sorbents on fire. And we produced hundreds of samples in the past 10 years. Looking forward, thousands of more will come, very likely. Now, this is one way of doing it. we are doing that in our company, but many others are doing it. There are companies out there, startups, more established companies, and researchers and scientists. And that is a good thing, because the challenge ahead of us, that is immense. Now, let's step back and look at it at the big picture. So, where does this kind of technology fit into our overall fight against climate change? And it's important that first and foremost, the most important thing we need to do is and will always stay the drastic reduction of emissions of greenhouse gases. Without that, we will have no chance of ever meeting any of our climate goals. Then in a second step, it will be important that we can all ramp up the capacity of extracting and removing CO2 from the atmosphere. Now, when thinking about the latter, so far I've spoken about technology, but we shouldn't forget that also nature offers several solutions to extract carbon from the air, such as forests and oceans. And one element that is very important will be doubling down on these methods offered by nature, enhancing them and protecting them. That is important. However, will it be sufficient to rely only on nature-based carbon sinks? Very likely not. Trees need time to grow, and forests need space. And there's simply just not enough area available to plant entire continents of new forests, which we would need in order to capture many billions of tons of CO2 from the atmosphere. And therefore, besides preserving all these nature-based solutions and enhancing them, it will be very important to scale up technology-based solutions for large-scale carbon removal from the atmosphere. Now, I often get asked, if you build direct air capture plants like the one we saw before, is that a license to continue polluting? It is clearly not. Direct air capture is not a silver bullet, but it is a must-have. Had we stopped emitting 20, 30 years ago, or at least substantially reduced our emissions, Climeworks and this whole emerging industry around us would likely not be here today. And for the climate, that would probably be the better solution. However, that's not where we are today. Today, the IPCC has indicated in their last report that technology-based solutions to remove carbon from the air are a necessity, and they included it into their models. And that is why this entire industry that is currently emerging now needs to double down on moving from small scale and relatively expensive to larger scale and cheap. Double down on developing, deploying, learning, and adjusting in the field. We have to develop markets, we have to develop policy, and we have to develop mechanisms to analyze the CO2 capture and other technical ways of removing CO2 that take care of the fact that by taking CO2 out of the air with machines and putting it down on the ground, we have one of the most permanent ways of storing the CO2 away for millions of years. Now, let's get back one step and let's get back to today, where we are. Let's get back to the present, to what is concrete. Let's get back to Iceland and our Orca plant. I've told you before how these collectors extract CO2 from the air. Now, how do we make sure that it really permanently stays locked away? For that reason, in Iceland, we've partnered up with the company Carbfix that have developed a method for permanent carbon storage through mineralization. What they do is they take the CO2, mix it with water, and inject it into underground volcanic so-called basalt rock formations. That is one of the most abundant stone material that you find on Earth. And by doing so, the CO2 binds with the rock, it mineralizes, and it literally turns into stone within 2 years, hundreds of meters underground. The good thing about that method is that it is very tangible and it's very easy to understand. And for that purpose, I've brought this rock sample here for you that is taken actually from a drill core of a basalt rock formation hundreds of meters underground. And what you can see here, that's a black rock, which is the black basalt rock containing some white crystals. And these crystals are CO2 turned into stone underground and locked away. Now, I explained to you one method of doing this. There are several other methods out there. There are several other techniques, other technologies, but the important thing about it is that this thing is out there. It's in practice, it's operating, and we are learning from it. And that is so essential for this new industry. And we have learned a lot, actually. We have learned how to operate on hot, dry summer days. Learned to operate them in pouring rain. And we even had to learn how to operate them on a just normal day. We had to learn how to ramp up the Orca plant immediately after an Icelandic snowstorm. And this all is what we need in order to deploy these plants all over the world. We should deploy them all over the world because we do need so many of them. We can deploy them all over the world because the air is everywhere around us, and the CO2 is almost the same concentration everywhere where we are. So it doesn't matter where we capture the CO2. And for that reason, and in the spirit of deploying more, in June of this year, we have announced the next step on our Climeworks scale-up roadmap, which is named Mammoth. And that is what you see here. That is a plant which is 9 times larger than the Orca plant, that will be in Iceland as well. And the first tons of CO2 will be captured by the end of 2023. This winter, we will finalize the first building before the snow starts. Now, that is a big challenge ahead of us. And actually, you can only really understand what this challenge is and really quantify it if you build these things out there, make mistakes, and learn from them. So it's a hard problem. It's not a simple problem to solve, and there is no easy solution to it. But without action like this, there is no solution at all. And so when I started looking back at the last 15 years, what we have been doing, I'm now looking forward to the next 15 years that are to come, because that is what we need. Thank you.